A lattice walk is a sequence of consecutive steps that are of a particular type. More formally, it's a regular arrangement of points in a Euclidean plane. Lattices also exist in higher dimensions, but for this class, we're mostly focused on just a plane. And there are 5 different types of lattice grids, but the most common one is the one on the next slide. A lattice walk starts with a lattice and a step set, and a lattice walk is a sequence of allowed steps moving around the lattice. For instance, here is a lattice walk using the steps up, down, left, and right. It has 12 steps or is of length 12. This is another example of a lattice walk using a slightly different variation of arrows where you can go diagonally. Most of the problems that we've shown has used a square lattice walk, but this one is hexagonal. It uses a similar step set, and you can use the step set shown to move across the grid.
There are also alternate ways that you can use to depict your step set. So far we've been using arrows such as up, right, down, and left, but you could also use coordinate directions such as north, east, southwest, or coordinates, so 0, 1 indicating you move 1 up, 1, 0 indicating you move 1 to the right, 0, -1, and -1, 0. And then you can also introduce another aspect, such as you could make some of your steps different colors. So in this last step set, you can either go up and make that step red, or you can also go up and make that step blue. One of the other things with lattice walks is there's a lot of interesting restrictions you can apply to them. So first off, we have one fairly common restriction, which is called a dike path, and it uses this step set here, which is up and to the right and down and to the right. And the restriction on this path is that it never passes below the x-axis. So you can see a picture of one here in figure A. So it moves either up and to the right or down and to the right and never passes below the x-axis. Another restriction would be a self-avoiding walk. So this is a walk where the steps you choose will never revisit the same point or never cross back over on itself. So these are shown in figure B. The one on the left is a self-avoiding walk because this never revisits the same point twice, whereas this walk on the right is not a self-avoiding walk because, as you can see, it does backtrack and revisits the same point multiple times. Other interesting problems you could have is by involving an endpoint restriction. So you want to figure out how many paths go to a certain point mn, or have different restrictions to your step set, which we've shown some of that in these examples. And you can also have lattice walks that you want to try and pass through or avoid a certain point in the lattice, such as the point 1, 1. You want to find all the lattice walks that either go through this point or that do not go through this point.
Also, another feature of dike paths is that they end at the point 2n, 0, so it's always an even number of steps and always ends back on the axis.
Special lattice walks. There are 3 special types of lattice walks that show up in the literature. First one is self-avoiding walks. Second one is dike paths. And third one is mosaic paths. By definition, a mosaic path is a lattice walk in the Euclidean integer plane from 0, 0 to n 0, which never pass below the x-axis. Its permitted steps are up step 1, 1, down step 1, -1, and the horizontal step 1, 0. If you allow horizontal steps at any position in a dike path, what results is a mosaic path. For example, the figure 1 is an example of a mosaic path of size n to 11. And we denote the up step by red symbol and the down step by green and horizontal step by blue. You can see that the red is up step, the green is down step, and the blue one is horizontal steps. And in totally, this Mozarkin path has a size n is 11. This is another example. There are 9 Mozarkin paths of length 4. Those 9 pictures are different situations of Mozarkin paths of length 4.
How many lattice walks begin at the point 0, 0 and use the steps right and up and end at the point mn? Because we are only allowed to take right and up steps, we know that to reach mn, the total amount of steps needed is m plus n, where m of those steps need to be to the right and n of those steps need to be up. One way to count all possible walks would be to choose when to make each up step, with the rest of the steps being right steps. We can take a set of individual steps and choose n steps from this set. These will be our up steps. The rest of the steps will be right steps. There are m plus n choose n ways to choose when to make an up step. Using our example, we have a 7x4 grid. From our total required 11 steps, we choose 4 steps to be up steps. We have drawn out one possible lattice walk of the 11 choose 4, or 330 total lattice walks possible on this grid.
As an interesting example of lattice walks, I want to talk about dike path. As a motivation, assume you are in a pyramid with a maze. Maze means for us that paths go only 45 degrees forward upward or forward downwards with 45 degrees. Half of the pyramid is underwater, which means everything lower than your starting point is underwater. In the end of your walk, you want to reach the same height as in the beginning. The question is now, how many different paths are there? A math formalization of the problem are dike paths. Let's talk about some examples. We need as many up forward steps as we have down forward steps, and each up step must come before a down step. In particular, the total number of the steps must be even. For 2n equals 2, we have only one such path, which is a head. For 2n equals 4, we have 2 such paths, which are 2 connected heads or a head of double the height. For 2n equals 6, we have 3 connected heads. One head of triple height, one big followed by a small head, one small head followed by a big head, one double peak. That's 5 in total. For 2n equals 8, we have shown in the homework that there are 14 such paths. This counting sequence continues. The answer will be presented in the course of the lecture.
Something that I find interesting about lattice walks is that I've seen them before in everyday life. I personally use a bullet journal to stay organized, and I'm a bit of a perfectionist. I would do similar problems that I've seen in homework by figuring out how many boxes I could fit into a page and what size they could be. I wouldn't necessarily do a typical math problem, but counted boxes and saw the different ways to arrange it.